Continuing section 7.3 on collisions in one dimension, let's look at this example of a ballistic pendulum. So this is a classic physics example because it highlights conservation of momentum and conservation of energy all at once, and how those two concepts can be applied to different scenarios and can actually work together to accomplish solving a problem. So we have this block of wood that's hanging, and then we fire a bullet at it, and we see how far does that block of wood swing into the air. So it says here that the mass of the block wood is 2.5 kilograms, the mass of the bullet is 0.01 kilograms. The block swings to a maximum height of 0.65 meters above the initial position. So it swings up once the bullet enters it, right? Just knowing how high it swings and those two masses, we can figure out the initial speed of the bullet, assuming air resistance is negligible. So that can tell us the muzzle speed of the gun that fired it, for instance, which could be useful if you're into crime scene investigations, if you're trying to work backwards, that could be a useful approach. Or maybe in an alternative problem, you already know the bullet speed, but you want to know how high something will fly into the air. So that's the type of thing we can see here. So when we're looking at this, we notice that there's a few different points of interest, right? First, we have the bullet as it's fired, and it's approaching the block that's stationary. So the bullet's moving while the block is stationary. And then the bullet enters the block, and then the two of them swing together up to some maximum height. So what we want to do is label everything that's moving and not moving, right? So at the beginning, the bullet is moving, block is not, then the bullet and the block are moving together. And then at the maximum height, just as we saw in our kinematics chapter, when we reach the maximum height, the velocity is 0. It stops very briefly before swinging back down. So adding in some velocity labels here, right? We have the initial velocity of the bullet, v01. Then we have the final velocity of the bullet and the block together, and then they swing up to this maximum height as labeled. So this is a really nice labeling of the picture and all the details that were given to us in the problem, as well as adding in those velocities. So our first step is to look at the fact that the bullet is going to run into this block. It's gonna wedge in there, right? And we can assume here that the block is enough that the bullet doesn't just pass through. So that could be another interesting physics problem. But in this case, it should have probably specified that they do stick together and swing up. So as the bullet's coming into the block, that's a collision. What kind of collision would that be? Well, if we think about the bullet is entering the block and they're sticking together, that's our totally inelastic or completely inelastic collision. So since it's a collision, we don't have any other outside forces acting on the bullet or the block system as a whole, we can apply our conservation of momentum. So apply the conservation of momentum to the collision. And this is a great statement of the conservation of momentum. I really like this equation. This one's a handy one to include on your crib sheet because it focuses on both objects, their final and initial momentum, right? So mass 1 times its final velocity plus mass 2 times its final velocity is equal to mass 1 times its initial velocity plus mass 2 times its initial velocity. Now, as we look at the initial case, mass 2, the block, does not have any initial velocity, right? So V02 is just equal to 0. So that second term disappears, right? That's why this just becomes 0. The other thing to notice is that because it's a completely inelastic collision, mass 1 and mass 2 are both traveling at the same speed, Vf. So we could say here that Vf1 is equal to Vf2, which is equal to Vf. This is one of the really useful things about a completely inelastic collision. Because they're traveling together, they have to be traveling at the same speed. So if we substitute in Vf for both of these velocities, then we can factor it out and we just have the final velocity times the total mass. So we end up with this relatively simple equation. We know that we ultimately want to solve for that initial velocity, the speed of the bullet before it encounters the block. So if we divide both sides by m1, then we'll be at an equation. So we get that the initial velocity of the bullet is the total mass m1 plus m2 times the final speed divided by m1. And we know both the masses, so that part's good. What about Vf though? We weren't actually given that in the problem. So that still is a bit of a mystery at this point. It's something we need some more help to figure that out. What else did they give us in the problem besides the masses? The other thing they gave us was this final height. If we think of that we have speed and it gets converted to height, what does that get you to start to think about? What might we be able to apply here? I'm not going to do momentum here because it's not a collision of some sort, but there's something else we can use. The trick here for the second part is we're going to apply the conservation of energy to the swinging motion, right? We're going to go from at the bottom when we have velocity, that's where the bullet and the block together have kinetic energy, and then it swings up to a maximum height where it briefly stops. So the kinetic energy goes to 0, and it all becomes what form of energy? It all becomes potential energy. And because it says air resistance can be neglected, which is very reasonable for a block that's swinging not all that far, then we can set the initial kinetic energy equal to the final potential energy. And that's exactly what this equation here is showing. It's showing the potential energy final is equal to our kinetic energy after the collision. So mgh for our potential energy is equal to 1/2 mv squared. Now we have to be careful here. What masses are we talking about? Well, we're talking here about post-collision, right? In the middle is the collision. This is all the swinging. If it involved the collision, we wouldn't be able to use conservation of energy because we lose energy in the collision. But now that the collision's happened, we're able to conserve energy. And so the mass is just going to be the mass of both the bullet and the block together. In both cases, m1 plus m2, m1 plus m2. Once you recognize that it's the same mass on both sides, that will divide out from both sides. So you don't need to worry about that too much. So that divides out, and we're left with g times h final is equal to 1/2 the final Vf squared, where Vf is the final velocity of the initial segment. So a little confusing which final are we talking about, but that's okay. So to solve for Vf, we'll multiply by 2 and take the square root as shown here. And so we know the height, we know g, so we could calculate the final velocity after the collision with the square root of 2 times 9.8 meters per second squared times 0.650 meters. We could get a number here, but this isn't ultimately the number we're looking for. What we want to do instead is take this result and we're going to combine it with that result from our conservation of momentum. So that's what we're going to do for our very last step where this is all coming together. So we'll take this Vf that we just calculated, plug it into the equation that we got in the conservation of momentum, and then put in our masses, and we can calculate this, and it comes out to 896 meters per second. And it is positive because we are continuing in the positive direction. Now, when I saw this number, I was like, that seems really big. What is that in miles per hour? It turns out this is about 2,000 miles per hour, which is really fast. So then I was like, okay, this must just be made up numbers. That seems way too fast. But it turns out rifles have a muzzle speed which is that velocity that leaves the barrel of the rifle, between 1,200 and like 2,800 miles per hour. So this is right in the middle. It's actually a very reasonable speed for a bullet leaving a rifle barrel. And we were able to calculate it by noting how much the block swung into the air. Very low-tech solution, but very cool to get to see it. And we will get to see a similar example in a lab in just a few weeks, where we take a look at a different bullet and block arrangement, but get to study some of the physics and what is conserved and what is not conserved. So that should be interesting. I'm looking forward to it. Hope you are too. We will wrap this example up right there.